Hey, what's happening, folks? All right, so today we are going to go through the next unit, which it has to deal with search algorithms. And there are two main search algorithms that we're going to cover tonight, and they have to deal with binary search and linear search. When to use them, when not to use them, how you can use them, etc. All right, so binary search out of the two is the most efficient system between them. Binary search takes advantage of the fact that when you have ordered lists or ordered data, you can easily comb through the list of data in order to achieve your target, meaning you can find the information that you're looking for. And the way that you would effectively do this is by finding the midpoint of what you're looking to search for, and then determining if the data set you're looking for is lower than that midpoint or higher than that midpoint. So when you are lower than that midpoint, or if the data is lower than that midpoint, well, that means any number that is beyond that midpoint you don't need, because the data is below it. So you can pretty much cut half the list off immediately, and then you could hone in on the lower half, and again, you would do the same thing. You could focus on the middle of that lower data set, and if that number is still too low, well, then that means the number from that midpoint and up you can get rid of. And you can keep doing that over and over again, whether it be lower or higher, by always finding the midpoint of the remaining data set. You can easily chop off a half of a half of a half of a half until you can zero in on the target in question. So the example that we're seeing over here is we have numbers 1 through 16. All right, and so again, you can choose any number between that, and you can even kind of do this in your head as we're going along. But whatever target number you choose, the first question that you're going to guess, or the individual who maybe needs to guess your number, you're going to start off with the number 8. All right? So if we had a 0 there, instead of just starting with 1, it would be 0 through 16, and 8 would be the middle number. But as of right now, you can either choose 8 or 9, being the middle number. So let's just say, for example, that the target number I choose, as you can see as it goes down, is 13. And I start with number 8. So I'll guess your target number is 8. And the individual will then turn and say, nope, that's too low, because I'm trying to get to 13. So that automatically means any number that is below 8 I could totally get rid of, even the number I chose, because I know that 8 is not the correct number as well. So I can take numbers 1 through 8, I can just take a knife, chop them off right between 8 and 9, and I can just totally get rid of that entire beginning data set. And so what that leaves me is with numbers 9 through 16. So again, remember, the target number is 13. So I look at numbers 9 through 16 and I find the middle point. All right, and so again, the middle point could be either 12 or 13. So if I chose 12, well, then that means I would then ask the individual, your number's 12, and they would say, nope, too low. So then that means any number from 12 or below is now not within range, or not in the target. So I can get rid of all of them. And that would then leave me with numbers 13, 14, 15, and 16. All right, and that was only guess number 2. So my next guess, again, I could either choose 14 or 15. So if I choose 14, the person will then say, nope, that number is too high. So that automatically means I can get rid of 14, 15, and 16, and there's only one number remaining, and so therefore that one number is the target number in question, which is number 13. So throughout the entire process, as you can see, I solved this problem within 4 guesses. And so from this is an example of binary search and how we're basically using that methodology or that algorithm to whittle down your data by taking a half of the data set, finding out which half your target is within, and then getting rid of the other half. And then you do the same thing again and again until you get to the item or the data that you're looking for. So looking at an algorithm for binary search, this is something what it would look like. And again, this isn't the only way you can write a binary search. There's many ways that we can actually go about doing it. But for right now, looking at this one, as it says, we're going to repeat the process, as you saw within that previous example, until we find the correct number. Or if we keep running, or if we run out of guesses, then we have to let the individual know that there's, the target list or the target data is not found. So what we're going to do is we're going to start off by guessing the target number, which is the middle number within the entire list. And that's when we decide if the guess is too high, then we're going to cut the top half of the list off, or if the guess is too low, then we're going to cut off the bottom half of the list. Or if the guess is correct, then we've hit the target, and so we need to stop. And then lastly, if we run out of all the numbers that are within our list, all right, then that means that the target that we're looking for is not present, and so we need to let the individual know that nope, your guess or your target is not found. All right, and so how do we now think of this from like a mathematical perspective? Well, because of the fact that it's a binary search works off of the same structure that binary numbers worked off of. So if you remember back from the binary number unit, we looked at the base 2 system. And the base 2 system is just 2 to the power of n. So however many numbers that we have. All right, and so what that power means, that power is important because that power determines or it matches to the number of guesses that we need, which is matching to that target number in question. So if you look toward the bottom, we have a chart of x and we have the chart of 2 to the x power. So the chart x is 0, 1, 2, 3, 4, 5, 6, 7, 8. As we go down, that is the number of guesses that we would need to guess the number that is directly to the right. So again, binary code always starts with 1 and then goes to 2, and then because it's base 2, goes to 4, 4 to 8, 8 to 16, 16 to 32, and so on and so forth. And if we look, remember, this is not, this is not 0 to the power of 0 or 1 to the power of 1 or whatever. This is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on and so forth. So what this is telling us is that if the target number, if I have 16 numbers, 0 through 16, or 1 through 16, I should say, and I want to guess the optimal number of guesses to find the target number, well, I would then use the base 2 of that, which would be 2 to the 4 power, which would equal 16, and that 4, the number, is basically the number of guesses that I would need in order to reach that target number. All right, so that would be how many searches we would go through. So if we work off of the binary system using binary numbers, it's very nice, very easy, very whole numbers with a number matching with the number of guesses. But what happens now if we find somewhere in the middle, like n, if we set n to be 100? Well, the problem is that, as we go forward, we use, 2 to the base, or the base 2 to the whatever power. Well, in order to go in reverse, we would have to basically take the log of that number in order to get that base power back into the base in question. And so if we take the log of the base 2 log of 100, we would get a value of 6.64. Now, obviously, that's not a whole number, and we can't have 6.64 searches or guesses. So what we would have to do is we'd have to round, and we'd have to kind of sacrifice and take that extra hit of that extra guess in order to make sure we find the data set that we're looking for. So in the case of 100, we would need a total of 7 guesses. So there's no difference or discrepancy between the value 100 or the value 128. You would still need a total of 7 guesses in order to reach that value. So that's basically how that works. And that number, that will hold true no matter what number that we use, whether if it is base 2 convenient, as you see within that list there, or if it's some number in between. So the other type of search mechanism is the linear search. One thing I should have said, and maybe I might have, but one thing I should have said here is that in order for binary search to work and to work well, is that your data set needs to be ordered. If you do not have an ordered data set, then it's going to become very tricky, if not, I don't want to ever use the word impossible, but it's highly unlikely that you're going to be able to reach the outcome efficiently if you are working with a non-ordered data set. So again, like the previous slide where we had the numbers, all right, the numbers 1 through 16 are nice in order, so it was very quick and easy for us to kind of track down within 4 guesses the number in question. In the case of jumbled numbers, well, it won't work as well because if you have these numbers jumbled over here and you chose the midpoint, which the midpoint happened to be 3, and you said, nope, your target number is higher, well, what happens if you have higher numbers on either side? We don't know which direction to go in. So whenever we have jumbled numbers, binary search starts to break down. So this is where linear search comes into play. So unlike binary search, all right, linear search is straightforward. The word linear means straight line. And so what we're doing with our linear search is we're starting with the very first item that is within our list, and we're going through every single bit of data until we recover or we find the item that we're searching for. So that's good because it's very thorough, which means we are definitely going to find the number. It's bad because you go through every single data point, and again, going through every single data point means that you could be going through hundreds of bits of data as opposed to just 7, which would happen in a binary search. So linear search is not as efficient as the binary search is. So with linear search, though, you could have an ordered set. And you could search through an ordered set, but I don't know why you would, because binary would be definitely the way to go. But linear search can only be used when you have a non-orderly set, which binary search you can't. So, if you're dealing with a non-sorted list, then linear search will have to be the option that you do. All right, so... But what happens now if you want to increase the efficiency of this, and you have lots and lots of data that you have to kind of go through and search? Well, then the best choice obviously would to create an ordered set or to sort your data, and then once your data is sorted, you can then go through and do a binary search and then find it much quicker. So it's just kind of showing us, with linear search, before our data is sorted, we have a deck of cards here, random numbers chosen and randomly placed within each cell. And if I needed to find the number 3, we'd start with the very first one, and we'd literally count through every cell until if target equals 3, if target equals 3, if target equals 3. Oh, here it is, target equals 3, therefore return the data. If I spent a little time sorting through my data, writing an algorithm that would sort the information, what I can do is I could place all the information in a sorted list, starting from lowest, which I'll say is the ace, and then increasing up to the highest, which would be the king. And then what I can do is I can assign an index value to this data. And so this index value over here, 1, think of it as you have 10 buckets on a table, and you have a little poster card, and you put a little 1 on it, and you put it in front of the first bucket, and then a number 2 on the poster card with the second bucket, and a 3 on the third bucket, and so on and so forth. We then take all the A's, dump them in the first bucket, all the 2's in the second, all the 3's in the third, and so on and so forth. And then what we end up having is we have a not only a sorted list, but we have it indexed properly. So what I can then do is do a binary search on the index, because I know that index 1 is linked to the letter A. I know that index 9 is linked to the queen. I know that index 5 is linked to the 5, and so on and so forth. So looking at algorithms side by side between the binary search and linear search, as we see on the right-hand side there, we have the binary search, slightly different than the one that we just covered a little bit earlier. But as you can see through the binary search, we have we're starting with setting the low target number to 0, and then the high number equal to n, and then n could be any number, doesn't matter, whatever you assign it. And then the middle is going to be nothing more than adding the low and the high numbers together and then dividing by 2. So if we have 0 and 100, we add those two together and then divide by 2, and then we have 50 as our target number, or I should say as our middle item number. All right, and so what we then do is we need to start asking those high-low questions, and we're going to repeat this process until the middle number is either equal to the target or the low number is greater than the high number, which means we did not find the number we're looking for. So the questions we start asking now is, if the target number that we choose is less than the middle value that we just calculated, then what we need to do is we need to set the high number equal to middle minus 1. So for example, if my target is 30, and based off of 0 and 100, I start the middle is 50. Well, 30 is less than 50. So we're going to do that next line of code there. So if the high, we want to take the high number, we want to set it equal to the middle net value, which was 50, minus 1. All right, and that 50 minus 1 gives me 49. So now the high number, rather than starting off as 100, we're now saying the high number is equal to 49. So we're only now looking between 0 and 49. We would skip over this next line of code because, again, our target value is not greater than the middle value. It's still lower. So we would go through this. And we have a repeat block here. So we're going to keep repeating this process until the target number is basically that middle value. So we'd ask the question again, is the target less than the middle? Well, 30 is less than 49. So we're going to set the high number equal to the middle value. So we now need to find the middle point. And so the middle point between 49 would then put us at 25 or 24.5. So we round that to 25. So now when we get to that point, 25 is our middle number. Our target number is still 30. So in this case, 30 is greater than 25. So we're going to take the low value, which is 0, and we're going to take that middle point, 25, and we're going to add 1 to it, which is 26. So now we've effectively zeroed down the numbers from the low of 26 to the high of 49. And then again, we calculate the new middle point, and we keep going from there. And then we keep narrowing it in until we finally get the middle value is equal to target. And then when it is, we say display found target. Otherwise, that means the low value is greater than high value, which means the number is not present. So we then have to say target is not within the list. All right, so those are the basically two algorithms looking over the two. Actually, I'm sorry, I got to go through the other one. That's a binary search algorithm. Linear search is very simplistic and straightforward, and all we have is a for each loop. So for each item in the list, we want to check to see if the item is equal to the target. So we go through block 1 for each item in the list. Okay, so we go through item 1. All right, is the item equal target? If yes, then display found target. Otherwise, we keep going. Block 2. All right, what's in it? Is the item equal to target? If yes, we found target. Otherwise, we keep going. And we keep looping through the structure until we finally get to the part where the item does equal the target, and then we say found target, and then we exit out of our loop, and then we just keep going on if there's any more code. But in this case, there isn't any more code. All right, so what I want to do now is I'm going to switch over to App Inventor. And sadly, when I videotaped this earlier, it did not save, so I'm redoing this video. So I'm going to have to kind of explain the UI, which I already built, even though I built it from scratch in the previous video. So it's going to be very simplistic, all right, as you can see over here. What I did the first thing is I went to screen 1, and I switched the align horizontal to center because I want to have everything in here center justified. The next thing that I did was I went over here to the left and I grabbed the label. And I grabbed and dragged the label and dropped it at the very top here, which I named it label intro. And then all I did was I went over to the text area here and I typed in, rather than text for label 1, I got rid of that and I typed in my guess is : and then left it like that. The next thing I did was I grabbed a second label and I dragged that label and dropped it beneath this label up top here. And as you can see, what I did was I renamed it to label guess. And then after I renamed it, I went over to this background color and I changed it to cyan because I just wanted a little shading in the background rather than just gray all the time. And then I went, changed the font size to 40 because I wanted the number to be a little bit bigger. And then I went down at the height. I changed the height specifically to 50 pixels because I didn't want it to be super huge. All right, so I stretched this out to 50 pixels. And then I went to width, and I did a fill parent on the width, so it stretched across. And then I text alignment, rather than having the 0 here on the label, I wanted the lettering to be within the middle of this label. So I clicked on this and did a center justify on the text alignment. All right, so that takes care of that piece. Next, what I have is I have 3 buttons. And the purpose of the buttons is to, as you're playing the guessing game using the binary search algorithm, is to think of a number, and then you start the game, and then, okay, is the guess, 50? So if your number is 30, well then 50 is too high, so we're going to click on the too high. It should cut down this number 50 into 25. Well, 25 is lower than 30, so then I would say too low, right? So these high and low buttons are there for the guessing game to start going through the algorithm to zero out and narrow down to the target number. When the target number is reached, we have a third button in the middle here called correct, and then that is to notify the user or the individual that I guessed the correct number. All right, so what I'm going to do for that, the first thing is I used a horizontal arrangement, and I dragged and dropped the horizontal arrangement right there. And as you can see on the right hand side here, what I did was I changed the height of the horizontal arrangement to 50, and I changed the width of the horizontal arrangement to fill parent. All right, and then what I did was back to back to back, I just took 3 buttons and I dropped 3 buttons, one after the next after the next. It was button 1, button 2, button 3. So I clicked on button 1 here, and I renamed it to button low. And then I changed properties here by just doing a fill parent on both height and width. And then I changed text for button 1 to the words too low. I repeated that process with the middle button. I renamed this button win. You could rename it to button correct if you want as well. But I did that, and I went down here. I changed the text to correct. And then I did the same thing with the height and the width. I changed to fill parent on both. Obviously, I'm going a little fast through this, so you can just kind of pause the video as you're doing this so you can kind of catch up. And then the last one over here, I changed button text for button, or I said button 3. I changed it to button high. And then over here in the text area, I typed in too high. And then the height and the width, I changed to both fill parent. So that would then equally have 3 buttons spaced out nicely within that arrangement there. And the last, well, not last, but the next thing I did was I grabbed another label from here, dropped it in here, and kind of like what I did with the very top, or I'm sorry, with this one over here, I took this label, I changed the name of it to label number guesses, because this label is going to specifically count how many guesses were made to find the target number, while this label guess is basically guessing the correct number that it needs, the target number that it needs to find. So this one down here I renamed to label number guesses. And then over here on the right hand side I changed the height to 30 pixels, the label of 30 pixels, and the width to fill parent. And then I removed text for label 1 here, and I put in guesses, space 0. And what I want to have happen, and I also changed the alignment to center as well. Because what I want to have happen is have the counter, have the guesses, equal, stay the same, but have the 0 change to a 1, to a 2, to a 3 every single time a guess is made. And that's it. That's all that we have to do for the arrangement. There was one last piece that I did, though. I grabbed the notifier. I dropped the notifier on the screen. I didn't worry about changing the name since it's the only one that I'm using. And the purpose of the notifier is to, when the target number is found, to let the individuals know, hey, great job, you found the correct number. And I found it in this many guesses. And that's it. All right, so I'm going to stop this video here. The next video, I'm going to go through talking about how we put the code together. So we'll see you in the next one.